Good morning to all of you. In previous sessions, we have seen computation of discrete Fourier transform by using FFT algorithms, that is DIT-FFT and DIF-FFT algorithms. So we have seen certain examples where we have computed 4-point DFT and 8-point DFTs by using DIT-FFT and DIF-FFT algorithms. In today's session, we will be discussing realization of discrete time systems. So here we are discussing realization of discrete time systems. So in the design of discrete time systems or digital systems, or you can say digital filters, the system function that we have seen already, that is nothing but capital H of Z, or the impulse response, that is nothing but small h of n, must be specified, right? If we have the equation for the system function, so from the equation of system function we can identify the realization of the given discrete time system. So basically realization means we are simply representing the given system by using some block diagram, right? So these basically these discrete time systems, or maybe digital system or digital filter structure, can be implemented or it can be synthesized in hardware or software form by its difference equation. Okay, so this difference equation can be obtained directly from the system function or from the impulse response. So each difference equation or computational algorithm can be implemented by using your digital computer or maybe special purpose digital hardware, or it can also be programmable by using some special programmable ICs, okay, integrated circuits. So in order to implement the specified difference equation of the system, the required basic operations are simply uh, there is any difference equation, that difference equation can be simply implemented by using, or it may comprises this basic operation, that is nothing but addition, right? First one is the addition, second one is the delay, and third one is the multiplication by a constant, right? Only these three basic operations are involved in any difference equation, right? So in order to implement the specified difference equation of the system, these are the three required basic operations, right? So if you are selecting any structure to determine computational algorithm, so it can be simply that computational algorithm can be simply identified by using the block diagram realization of the discrete time system. So the most common methods for realization of discrete time systems are direct method, then there is cascade, parallel, or uh, some state variable realizations are there. So we'll be looking the realization of FIR and IR systems by using most of these forms, that is direct, cascade, parallel, and some other forms as well, right? So as we have already seen, okay, so the generalized form of difference equation we have specified as y of n is equals to summation k is equals to 1 to n minus 1 aka y of n minus k plus summation k is equals to 0 to m bk x of n minus k, right? So here you can observe that we have already seen this form of difference equation. This is nothing but the generalized form of difference equation. So it generally specifies the input-output characteristics of the given discrete time system. So output y of n is dependent on the some previous or past output samples, as well as it depends on the current input and past input samples. Okay, so if you are substituting k is equals to 0, so it means x of n will be there. So x of n is nothing but the current input sample. K is equals to 1, so it will be x of n minus 1 and so on, right? Here you can see that as here this a is 0, okay, is simply taken as 1, or more compactly we can represent this equation as basically if I'm just taking all these terms uh, close to each other, that is if I'm taking the output at one side and the output terms at one side of the equation and input terms at one side of the equation, so specifically this y of n can be sent inside this summation, right? And you can take limit as k is equals to 0 to n minus 1, okay, 0 to n minus 1, but in that case this a0 should be 1. Okay, so this is the most generalized form of the difference equation, which can be used to represent the input output characteristics of the given discrete time system. Okay, so here it is the linear combination of input and outputs, right? So the current output y of n is equal to the sum of past outputs from y of, if I'm substituting k is equals to 1, so y of n minus 1 to y of last value of k will be n minus 1, so it will be simply y of n minus n will be there, right? Correct. So here you can, instead of taking it as k is equals to 0 to me, it should be 0 to m minus 1. Okay, as well as if I'm considering the current output of the system y of n, okay, so it is equal to the sum of past outputs, right, from y of n minus 1. Okay, so these past outputs are scaled by delay dependent feedback coefficient, which is nothing but ak, plus the sum of maybe future, past or present inputs. Okay, so these inputs are scaled by, again, delay dependent feed forward coefficients bk. Okay, why we are calling it as feedback and feed forward, that we'll see in next session when we'll try to obtain the basic building, when we'll see basic building blocks, as well as we'll be utilizing those basic building blocks to identify the realization of discrete time system from the given difference equation. Okay, so here this y of n is nothing but the output of system, which is dependent on the past outputs as well as present, past and future input samples. Okay, so these past outputs and these input samples are scaled by these delay dependent coefficients ak and bk, right? So if I'm taking the z transform of this y of n, so this can be represented as y of z, and the equation for it will be n is equals to minus infinity to infinity y of n into z to the power minus n, right? So just for example, if I'm here, if I'm replacing this y of n with this equation, okay, so what I will get, so I will get the equation for y of z as summation n is equals to minus infinity to infinity. Okay, in place of y of n I will write this summation k is equals to 1 to n minus 1 ak y of n minus k, right, plus summation n is equals to 0 to m minus 1 bk x of n minus k into z to the power minus n. Okay, so if I'm replacing this uh, y of n with this difference equation, right, in this Z transform formula, correct? If I'm changing the order of this summation and rearranging this equation, so what I will get, y of z is equals to, I'll get summation k is equals to 1 to n minus 1, right? If I'm taking this ak constant also outside this summation, So in bracket I can have this summation n is equals to minus infinity to infinity y of n minus k into z to the power minus n will be there, right? Correct. Similarly, I can write it down for the other term, that is if I'm taking this summation n is equals to 0 to m minus 1 bk outside this summation, that is summation n is equals to minus infinity to infinity. So I'll have x of n minus k multiplied by z to the power minus n. Right? So here you can again see that summation n minus infinity to infinity y of n minus k into z to the power minus n, it is nothing but the formula for z transform of y of n minus k. And as per the time shifting property of the z transform, we can write down the z transform of, or you can simply write down the z transform of this y of n minus k as y of z, that is z transform of y of n multiplied by z to the power minus k, right? As per the time shifting property of the z transform. So this complete equation can be replaced with this z to the power minus k into y of z. Similarly, plus summation n is equals to 0 to m minus 1 bk. Here it will be z to the power minus k, capital X of z will be there, correct? So here you can take the y of z terms on left hand side. So y of z, if I'm taking common, so in bracket I'll have 1 minus this summation k is equals to 1 to n minus 1 ak z to the power minus k, correct, is equals to, this will be as it is summation k is equals to, here it is basically k is equals to is there, right? So here it is summation k is equals to 0 to m minus 1 bk into z to the power minus k into x of z will be there, right? So we know that the system function h of z is nothing but y of z upon x of z. Okay, this is nothing but your system function h of z. So I can simply write down this equation as uh, if I'm taking y of z upon x of z, so this x of z will be sent on left hand side, this term we can send on right hand side. So I will have this summation k is equals to 0 to m minus 1 bk into z to the power minus k whole upon 1 minus summation k is equals to 1 to n minus 1 ak z to the power minus k, right? So if you observe this equation, right, so what I have mentioned in the previous slide, that this difference equation, okay, even in case of difference equation you have addition operation, you have delay operation, as well as you have multiplication by constant. So here you are multiplying it by constant. Even this can be observed when you have converted this difference equation in the system function form, that is h of z. Okay, so it comprises additions, it comprises delay, right, it comprises multiplication by constant. Okay, so only these operations are involved in any system function or in the difference equation, right? So there are basic building blocks for these operations, and by using those basic building blocks we can realize the given discrete time system, correct? So here the final h of z or system function should have this form, that is summation k is equals to 0 to m minus 1 is there, right, bk into z to the power minus k whole upon 1 minus summation k is equals to 1 to n minus 1 ak into z to the power minus k, right? So for realization of any discrete time system, the system function should have this form, where in the numerator we have this z to the power some negative values, right, multiplied by certain constants will be there. So these uh, coefficients bk are nothing but the coefficients which are multiplied with the input terms. Okay, that is nothing but uh, past, present, or future input samples, right? While ak are the coefficients which are multiplied with the output terms. Okay, so these are in the denominator. So output is in denominator, inputs in numerator, right? But in this system function, this first term should be 1, so that you will get the proper realization structure for the given system. So we'll be looking at the realization of FIR, that is finite impulse response system, as well as IR, that is infinite impulse response system, right? So in next session we'll be discussing the basic building blocks required for the realization of discrete time system, as well as we'll see one example where from the difference equation we'll try to obtain its realization structure, as well as we'll discuss the signal flow graph in the next session, and the advantages of representing the given system in block diagram, right? And we'll see the difference between canonic and non-canonic structure. Okay, so all these topics we'll be discussing in the next session. Thank you for joining this session.